Okay, so here is the 9 concepts. We're going to discuss number 2 and today, and number 4 probably on Thursday. And let's do a quick review of what we said last time. We talked about correlations of detector clicks. So we had this device, which we call nonlinear optical crystal. We sent very strong blue light into it. And rarely, but one time out of 10 to the 9 blue photons that go through, that blue photon is split into a pair of red photons. One hits the A detector, which is called the herald, and it clicks. The other one goes over to here, and it could either hit a detector, or it can first hit a beam splitter and go to one of 2 detectors, B and B prime. And we talked about these conditional probabilities, P of B clicks given that A clicked. We talked about P of A, the probability that A clicks, and we talked about the joint probability that both A and B click. And then we talked about this quantity called G2, which is the ratio of the probability that B and B prime both click, and then divided by the probability that B clicks and that B prime clicks, and all those are conditioned on the fact that A clicked. And we worked out some problems showing that we can calculate this based on the numbers N of the different kinds of clicks. And then Henning did a very nice experiment and showed that in this scenario, because there's only one photon ideally traveling in this path, this G2 quantity is approximately 0. Although we pointed out that for a laser, if I just shoot a laser directly at this beam splitter, that contains many photons, and each photon behaves independently. They are independent, which means they're not correlated. And it turns out in that case that the G2 is equal to 1. This represents lack of correlation, whereas 0 represents very strong anti-correlation or negative correlation. If B clicks, B prime does not click. Okay, now during the Jamboard session, somebody asked a very nice question. What would happen if I put a detector in both A and B directly? And I actually gave the wrong answer. So let's do the correct answer now, okay? You can work it out. And poll, share results. Good, most people selected the correct answer, which is the bottom one here, which is that the probability that both detectors click equals the probability that B will click, which also equals the probability that A will click because they all happen together. If B clicks, you know that A clicked as well, ideally. Okay, so very nice. Let's go to here, go to here. Correct, that is correct. So think about that. If you selected a different answer, think about why this is the correct answer. Okay, now Zoom poll number 3, which is correct. And we see that most people selected the middle option, which is that G2 is much greater than 1. And to move along quickly, I'll just say that that is correct. And where you can see that is that this G2 is the ratio of these 2 numbers. If PAB equals PB, then these cancel, and I end up with 1 over PA. But that's also equal to 1 over PB because those are equal. But PB is a very small number. Therefore, 1 divided by a very small number is a very large number. So what this tells us is that there's a very strong correlation. If G2 is very large, it means there's a very strong correlation. Remember, if it's a laser and you put a beam splitter in a laser, you get G2 as 1. And if we do the beam splitter in the heralded single photon, as we discussed earlier, in that case, B and B prime are very anti-correlated because there's only 1 photon. In that case, G2 approaches 0. Okay, now we go on to a new topic. There was a famous professor named George Stokes, who was a professor at Cambridge University in England back around 1900, and he did this experiment. He had a calcite crystal, which is a natural crystal you can mine out of the earth, and he had a light bulb and 2 black screens with holes to make a directed beam, and he saw that when there's no crystal there, he saw a single spot of light on a photographic film, and when he put the crystal in, he saw 2 spots, and we sometimes call these the upper spot view and the or the up spot and the down spot. Now, in those days, they didn't have click detectors, but they did have film, and film is kind of grainy. And if you shine very weak light onto it, you just see little specks that appear, more specks the longer you expose the film. And he exposed it for a short time, and he saw that there were little specks that were randomly either at the top or randomly at the bottom. Okay, so this is a cartoon of what's happening. If you put a light beam through the crystal, you know, part of it goes straight through and part of it gets deflected down to the lower beam. And so we say the crystal sorts these cases into two beams. There's some discrete property that light can take, and it has only one of two possibilities. And we haven't said yet what that property is. Okay, so it's, of course, we know now polarization, and it can be described classically very easily. And then it also can be described quantum mechanically. So let me just go through this quickly because most of you know this to some extent. Well, it has to do with the orientation in which the electric field is oscillating. And light, of course, is made up of electromagnetic fields, the same as radio is made up of electromagnetic fields, but with a different frequency. So what is an electric field? A field is simply an influence that establishes forces between objects that are not in direct physical contact. Before Newton, even during Newton's time, people had a very hard time thinking that two bodies that were not in physical contact, namely touching each other, could actually exert a force on one another. But Newton thought about gravity quite a bit. And he realized that when you drop a ball or an apple, it gets pulled towards the earth by a force, which we call gravity. Well, the apple is not in physical contact with the earth, yet it still gets pulled down. Nowadays, we understand that in terms of gravitational field. The earth creates a gravitational field that extends to all of space, and the apple feels that field as an attractive force. Of course, the apple also creates a gravitational field, but it's a much weaker one. Earth doesn't feel it so much. Okay, so now if the electric field in a light wave can be made to look like this, in fact, this is a screenshot from my book. These little lines here are the direction and the strength of the electric field. And if we have a metal wire over here, an electron, this spot here, can only move up and down within the wire. It can't move out of the wire to the left or the right. If a force is applied onto it, it can move up and down the wire. So here goes. The light field is traveling past, and this particle is a particle that would move this way if it were positively charged. Up here I say plus charged. A proton moving, if a proton could move freely in this region, it would move up and down like that because the proton with a plus charge is pushed in the direction that the electric field is pointing, or yeah, pointing. However, if we have an electron, which has a negative charge, it gets pushed in the opposite direction from the way the field is pointing. So I animate this, and you see it gets pushed oppositely. Okay. Now, what if the wire is vertical and the field is now horizontally polarized, as I've tried to draw here in 3 dimensions? Well, think about what's going to happen as this light field passes the wire. The wire is very thin, so the electron cannot move very much to the sides. It can only move up and down. So here's what happens, pretty much nothing. The force is pushing it side to side, but it can't move. Therefore, it cannot do any work. The electron cannot absorb any energy from the field. No motion, okay. But if the wire is now tilted so it's horizontal, yay, it can move again. All right. So by watching the way electron moves, we could determine the polarization of the radio wave. I said light wave earlier, it should be thought of as a radio wave. And that's in fact how your radio receiver works in your cell phone. There's a little wire in there, and as the radio frequency waves pass through the wire, the electrons in your little wire antenna get pushed back and forth. So now we can apply this to light waves or radio waves in this way. If we have vertically polarized light or horizontally polarized light, and they pass through this device we call a polarizer, which you all have now in plastic film form. I draw this as a cartoon in the book this way because I didn't want to confuse the non-physicists reading the book. And I will reveal that there's something like wires inside there which run the perpendicular direction from what I call the slots in the toy model. So you can see if the vertical polarized light goes into this film, it can push electrons up and down in the wires, and that causes the light to be absorbed. Meaning the energy is removed from the light because the energy has been transferred into the motion of the electrons. So it gets absorbed and blocked. It's not deflected. The energy actually goes into the film, and the film heats up a little bit. But if horizontal light goes through, the polarization is perpendicular to the wires, so the electrons cannot move. So the electrons cannot absorb energy from the light, so the light passes through. Oops. So that's what happens. Excellent. Okay, so with that in mind, we have also the concept of dipole, which is diagonal polarization. And if you look from over here with your eye, look that direction, you see the orientation is diagonal. Now, I had this little cartoon picture, which I call direction indicator. It's kind of like a compass. This needle can point in any direction, right? And it can point to the northeast or to the north or to the east. But if it's pointing northeast, it's kind of a combination of north and east. And here's a little picture of a little vector addition diagram. And then there's the same picture. We call that the dipole is a combination of H pole and V pole. And so here's like the little schematic cartoon. So here's like a representation of the thing. Here's like a sketchy thing from the edge, and here's a mathematical way to represent the polarization vector at a certain time. The arrow is pointing up like that. Of course, we also know that it oscillates back and forth. Okay, so this is dipole. If it points down here, it's called negative or minus dipole, but that's really the same thing because it's oscillating back and forth. Okay, good. Moving right along. Katja from the Q-Tools company sent me a pretty cool video from the movie Despicable Me, which little kids like to watch. And one of the characters says this: a vector is a quantity represented by an arrow with both direction and magnitude. Now I'm going to have to go there. Unfortunately, my link broke. Despicable Me vector. I hope we find it here. Yep, that's it.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Doing a demonstration. Oh, nice. It's so difficult sometimes to get the line back inside.
Oh, how do I get out of here? I'm stuck. Uh-oh. Now we have sound effects. Hey, this looks pretty good. Okay, never mind. Okay, so that was a cool little video. I thought direction and magnitude. This is really great for, say, high school kids or middle school kids or elementary kids or people in my age group. Now, the next thing I like to do is show a different little movie. It's a program that I wrote in Mathematica, which illustrates the concept of in phase and out of phase. Okay, so let's go over to the Mathematica. So I hope everybody can see this. Let me know if you can't, Amy. So over here we have the field direction, which is pointing to 0 right now. And over here we have two graphs. Time is on the horizontal axis. The amplitude is the H component and the V component. So if I put in a little bit of of H component, and then I turn on the animation, yay, it oscillates back and forth like that. Okay, now if I turn that off and put in instead a little bit of vertical, and I need to put a 0 in here, and then animate that, of course we have the vertical polarization oscillating with this frequency of whatever. If for light, that vector would oscillate about 10 to the 15 times per second. So this is slow motion. And you can see as time goes on, the amplitude goes negative, positive, negative, negative, positive, 0, negative, 0, positive. So this is tracking what that's doing. Okay, now if I have a little bit of both, equal amounts of both, I can make anti-diagonal like that. Or if I rotate it this way, I can make them in phase. See, now they're in phase, they're oscillating together. So they're adding both positive, both negative, both positive. And again, when I put them out of phase, you see, when one is positive, the other is negative. So see, positive, negative, negative, positive, etc. And of course, I can go in between as well. I can go like that, and I can rotate that polarization to any angle I want just by changing the relative amplitude of the horizontal and the vertical. Very good. So that's what these pictures mean. When I show a picture like this, you should imagine that it's oscillating back and forth. And this is the in phase condition and the out of phase condition. Now notice that in order for these pictures to be stable, reproducing, the phase relationship has to be stable. We call that coherence or coherent, which means that the oscillations are synchronized. So we'll get back to the word coherent and coherence later. Okay, so now here's some cartoons of polarizations. Here, the black lines are the slots and the green lines are the wires. And I don't draw the wires in any of these pictures, only the slots. So I'm showing that H polarization can go through and V polarization gets blocked by the slots. Here, if I just have H polarization, it goes through as H. If I have a V vertical polarizer, only the V goes through. And if I put H light into a vertical polarizer, no light goes through. Yay. Okay, here is a simple Zoom question, poll question, which I will run. Number 5.
We don't see the poll question. Oh, it's here now.
Okay, thank you. Okay, 5 seconds. 4, 3, 2, 1, 0. Share the results. Okay, most people said that no light comes through, and that is correct. Because in this first polarizer, V could pass through here, but then V would be blocked by this polarizer. So nothing would get through.
Dr. Raymer, before we move on, there's a question in the chat.
Do you want to read it?
Sure. Why do we talk about slots when the wires are really doing the work of the polarization?
The reason that I introduced the slots was because in the book, it was written for a more of a popular audience. And I didn't want to distract the readers with the details of the physics inside of the polarizer. And for example, with the calcite crystal, I'm never going to tell you how the calcite crystal works. You can read about that in a physics book, but just think of it as a device that does something that's useful. That's sometimes the way technology is. Thank you for the question. Okay, so we have no light comes through, and there it is. Vertical goes through, but of course it gets blocked. Now here's a new word, mutually exclusive. This word will come up later in the quantum context. H and V are considered mutually exclusive. In this case, they're perpendicular, and if a light wave is purely V, it's definitely not H, and vice versa. It can't be both H and V. Now it could be diagonal, which is a combination of H and V, but then if it's diagonal, it cannot be anti-diagonal. So there's always things come in pairs. If an object has one property, it definitely does not have the other property. Although in quantum mechanics, it can be in a superposition of different ones. So we'll get to that more later. Mutually exclusive is the important word. Okay, here's a zoom pole. So remember, a watt is a unit of light brightness. For example, a 100-watt light bulb. Zoom pole 6. I will just go to the pole. You can read it yourself. Notice that the light beam is 1 watt here after this polarizer. And notice that this polarizer is oriented as an anti-diagonal polarizer. I didn't say that very clearly, sorry. This polarizer is actually rotated by 45 degrees. I'm sorry. This is an apolarizer. I'm sorry. It produces light here. This is the light vector. It's at A polarization, and then it hits the V polarizer. Okay, we have quite a few answers here. That's good. Share the results. Okay, most people said that it would be half a watt would be emerging here, and it would be V polarized. So that's interesting because the light was prepared with this polarizer to be anti-diagonal, as I'm shown by this blue arrow, and it has a power of 1 watt here. When it passes through the polarizer, it has the wrong orientation, so not all of it gets transmitted. So almost everybody said half a watt, that's correct. But some people said that the light here would be V pole, which is the same as this polarizer. And some people said the light here would be A pole, which is the same as the original A preparation of the light. So that's a very interesting question, which I want you to think about. Remember, we can decompose, or rather we can represent this apolarization as a vector sum of vertical and horizontal. So you can think of this blue oscillating arrow as two oscillating arrows, one going vertically and one going horizontally. So now think about that. What's going to happen when it goes through the V polarizer? What I'm going to do is I'm going to stop sharing. I'm going to run this poll again. Please answer it again. And remember, the V polarizer blocks the H component. The polarizer does not allow H light to pass through it. And the light entering the V polarizer is a combination of H and V. So you can change your vote right now if you want. And I'll stop there. Okay, so a number of you still held to the idea that the light here would be A, but that is not correct. The light here is V, because although it was A coming in, if you decompose it into V and H, the H part is blocked by this V polarizer. And so what comes through is only the V component. So think about that. There it is, V. It's very important to get this point, because a polarizer not only blocks and transmits a certain fraction of light, it also ends up changing the polarization of the light that gets through it. So A polarized light went in, and a smaller amount of V came through. The transmitted light wave is now polarized vertical. Very important. So I want to make sure you understand that. And if not, keep thinking. So this is just a summary of the four most important kind of polarizations that we'll be using. And then pointing out that direct sunlight is coming in a form that has all polarizations mixed together, infinite number of different polarizations all mixed together. And there's no coherence in that light either. So therefore, we can say that a calcite crystal is a device that sorts light by its polarization. So now we're back to the calcite, not the polarizers. So the polarizer blocks one and transmits the other. The calcite crystal is nice because it actually transmits both, but in a different beam path. So if we have unpolarized light here, say from the sun or for some other unknown polarization, it passes the H pole in this beam straight through, and it deflects and redirects the beam for the V pole. So if this light had an equal amount of H pole and V pole, you'd see 50 of the power hitting these two spots. But it could be different. It could be 30-70, or it could be anything. Okay. Now, if I rotate the crystal just by 45 degrees, the same crystal just rotated. So my arrow indicating the crystal axis is pointing at 45 degrees. We now call this a D/A oriented crystal. And we use the word measurement scheme to refer to how the crystal is oriented. So in the previous one, this would be called an HV oriented measurement scheme, or just HV measurement scheme. And in this one, this is called a DA measurement scheme. So you see, we're measuring different things. Here we're measuring the amount of light in the A pole versus the D pole. In the previous case, we're measuring the amount of light in the H pole versus the V pole. Those are different kinds of measurements. And in quantum mechanics, you always have to specify what you're measuring, because you cannot measure everything at the same time. Okay, so here is a thought experiment. It's not in the form of a Zoom poll. I just didn't make it a Zoom poll. So just think yourself, and if you have a pencil, write down on paper what you think the answer to this question is. This crystal is oriented in the HV orientation. So we say the measurement scheme is HV, horizontal, vertical. And here's two detectors over here. And I'll try to move along quickly because I think we're going slowly. So here's the answer. In this case, because it's a pole, it's made up of equal parts of H pole and V pole. So it splits those two into equal amounts of light power. Okay, so I'm trying to go through lots of examples so you can get the feel for this. Now we're going to go over to my laboratory setup. We have this nice setup that we use for this class. We have a helium neon laser, which shoots a red beam of light over to this mirror, which bounces off another mirror. And we have knobs here with screws in them so we can direct and steer the direction of the beam very precisely. We go through an aperture, which is just a piece of metal with a small hole in it. And we go through a calcite crystal and then maybe another aperture. These apertures are nice because I can open and close them. So I can remove the apertures just by opening it like a camera shutter. And initially I'm going to show here with no calcites, and then I'm going to put in one calcite and maybe another calcite. And then we have a lens which has the effect of making the spot look larger on the screen here. Now, when I show the picture, the spot's going to look white because I have a red card over here. For some reason, the camera makes it look white. Okay, so I'm going to move.
Dr. Raymer, your camera is off.
What's off?
Your camera, in order for the demo.
Do I have to stop sharing? Oh, my camera is off. Oh, thank you. Now my camera is on. So is that a good view of the apparatus, Amy?
Yeah.
Excellent. I'm just using my laptop camera to give you the view of it. And now I have my little setup here. So what we have, as you can see, is the laser beam is coming over here. And now it's coming over here, and now it's bouncing off that mirror. So now my laser beam is over here. And if there was a lot of dust floating in the air, you could see this laser beam, but there's not, so I have to move this card here. And it's also over here, and here's my lens, and now it comes over here and hits my red card, which makes a spot that probably looks white to you, but it's actually a red light. Okay, now, if I put my calcite crystal, I have a giant calcite crystal here, which is just one that's mined out of the ground down in Brazil. And it has this kind of shape to it, which is the natural crystal axis of the calcite. If I place that into the beam over here, I believe you'll see that it splits into two spots. Yay. Now the question is, what are the polarization properties of these two spots? Well, I have a polarizer film here. You can see my little polarizer film. I'm holding it with my fingers. If I drop that in a vertical orientation, so it's a V polarizer, it blocks the lower beam, but it passes the upper beam. So that's, as I claimed earlier, somebody just arrived or just left. If I rotate, here's the two spots. There's the two spots. If I rotate the polarizer, I can block the upper beam. If I rotate it back, I block the lower beam. Now this crystal is not the highest quality, so what I'm going to do is replace it with a higher quality crystal. And you can see that the orientation is given by this little white line, vertical white line on the crystal holder. And it looks like it's rotated at 45 degrees on that white line. So let me drop that into this mount. Now we have a much higher quality image. Notice that now the separation is on a diagonal direction because this crystal is rotated diagonal. And also notice if I drop this polarizer in with the vertical orientation, what it does, it just makes both of them a little bit more dim. It doesn't actually block one. But now if I rotate this polarizer, so by 45 degrees, it blocks the lower one, lower left. If I rotate the polarizer to minus 45 degrees, it blocks the other one, the upper left. So since I had to rotate my polarizer in my fingers by 45 degrees, that means I'm now blocking or transmitting diagonal and anti-diagonal. And if I rotate it the other one, now it's doing the opposite, diagonal and anti-diagonal. So now my two beams are polarized diagonal and anti-diagonal, just because of the way I put the orientation of my calcite crystal in. Okay. I have another calcite crystal, which is oriented HV. You can see the white line is vertical there. There's one more demonstration here. And you can see my laser setup now. Okay, I'm demonstrating the laser setup. So what I have here, people are joining, I have a giant polarizer. We can see it acts like a polarizer. Okay, and what I can do, I can just set that over here on the right side into the laser beam. So I know whatever light is coming through there is now polarized. And I can test using a small polarizer here, which polarization it is. Okay, it looks like it's V, because if I rotate this polarizer by 9 degrees, it gets blocked. And if I rotate it back to V, it gets through. Okay, now here I have another small polarizer. I have now two small polarizers, you can see. And if I put this second polarizer in here by itself, I can also rotate it. I'm over here now and make it block or unblock. So I can block that, I can unblock that. Now, what I can do is I can rotate this so it's blocked. And now I have this third polarizer, right? I have the big polarizer, it's going through first, and then it's going through the second one over here, and it's blocking it. Let me go like this. It's blocking it. And for some of you who probably know this magic trick, but the question is, what if I put this third polarizer in between the two? Now, for those of you who know this magic trick, you know the answer. But for those of you who don't know this magic trick, I'd like you to take the three of the polarizers that you have and do that experiment yourself. So if you have a way of keeping your laser on and you can hold the laser mounted on a book or something, do that. But if that's going to be too much trouble, apparently you have to wrap a piece of tape around the laser. So if you don't want to fool with the laser, just hold it up to the lights in your room. So just hold up your polarizers up to the room lights and rotate them so they're perpendicular. So what's coming through is pretty much black, nothing coming through. And now make a little space between the two polarizers and insert the third polarizer in between those two polarizers and rotate that third polarizer in between the two perpendicular polarizers and observe what happens. And now try to figure out why that's happening based on what we've already said. We don't have a Jamboard for this. We'll just move on. Think about it. Does anybody want to pipe up, turn on your microphone and make a comment about this, what you observed? If you do, just go ahead and try it.
I see that the light does get stopped, but it also allows it to go through when I rotate it.
And what angle do you have to rotate it to see it go through?
45 degrees.
45, that's right. So does that seem in any way surprising? Why do I call it a magic trick?
But it's not all the light that goes through, right?
No, that's right. We're going to calculate how much light goes through in a minute. But some people find it surprising that if you have two filters, which are perpendicular, and they're blocking everything, then it seems a little bit strange that putting another filter in between would not just block more, but actually lets light through.
It just like when it's go through one filter, and when before it's go to the next, it just forget what filter is went through.
Yeah, that's right. It forgets. I like that. It goes to one filter, my first one, and it comes out with a certain polarization. And then when it goes to the next filter, it forgets what the previous polarization was. And it takes on the new polarization defined by the new filter, but of course with a lower power. I like that word forgets. That's a good way to say it.
Actually,
So I'm just going to, yeah, go ahead, bye.
I borrowed it from Richard Feynman.
Okay, Richard Feynman always had a good way to explain things. I remember that. So I'm going to demonstrate the experiment now for all of you. Here's the vertical polarization that goes through, because my first polarizer, my two polarizers now are parallel. But now if I rotate this polarizer here, it blocks it. And of course, now you know the answer. If I put in my third polarizer at 45 degrees, like this, I get some power going through. So I really find that to be amusing. Call it a magic trick. I put in something that blocks light and it makes it go through. I remember when my graduate school professor showed me that, he was really excited. He said, "Mike, look at this. This is incredible." I'm not sure I understood why he was so excited at the time. But you block something and it makes it go through. That's because, as Feynman said, the light forgets what its previous polarization was. Very cool. So this all works in classical physics because we're just dealing with light waves, but it turns out that all of these same effects can translate over to the quantum mechanical situation just perfectly, with one big difference. I shall now share my screen and go to there. Okay, I shall do this. Try to do this. Okay, so now do you see this new slide with the big blue rectangle on it?
We do.
Okay, good. So what we have here is a little bit more mathematical treatment. And what we're showing is that the diagonal vector, red, and Amy, you see my cursor moving?
Yes.
Thank you. So if we have a diagonal vector and the length of it equals 1, okay, so if anywhere you aim it, it lands on this circle. And if I figure out how much, how long this horizontal polarization is and this vertical polarization, it turns out they have a length of 0.71, okay? And if I wait for a little bit time later, this red arrow oscillates and pushes down this way. And now the length of the green and blue arrows are minus 0.71, if you like. And it's what we call minus D. But as I said before, D and minus D are really the same thing because they oscillate between each other. So here's a question. What does this sum equal? The square of 0.71 plus the square of 0.71. That would be the length of this red vector squared, correct? So can somebody calculate that and shout it out on your microphone?
1.
1, that's correct. Almost exactly 1, which it should be, right? Because I said the length of this vector was 1. Okay, just checking. These numbers, 0.71 and minus 0.71, they're called length factors, which is what some people call them. Now here's another case, anti-diagonal, where we keep the vertical length factor positive 0.71, but we just flip the phase at a certain time of the horizontal, and we make that minus 0.71, and now it's going to oscillate between A and minus A in time. Okay. Now we could also just rotate that D vector, so it's no longer pointing diagonal. I call it D prime. It's a rotated, used to be diagonal vector, but now it's rotated. Of course, I could prepare that just by rotating my polarizer and looking what comes out. And as Feynman said, it forgets what its previous polarization was, and it's going to come out D prime. Well, now the length of these factors here is 0.92 and 0.38. And if I compute that with a calculator, I get 0.999, which is equal to 1, basically. And I can have also, I can rotate the anti-diagonal from this point down to here. And the numbers I used are shown up here, 22.5 degrees. That's actually an angle we're going to use later in this course when we talk about a certain experiment. So I wanted to show this one. So now, again, the length of this vector is 1. Just has a different phase relation because we flipped this one to minus h. Oh, notice that's interesting. I can put the minus sign on the length factor. I could put a minus 0.92 here and just say h there, or I could keep the 0.92 as a positive, and I can put the minus sign on the h. So it's different ways to think about that. This is 0.92 multiplied by the minus h vector, which is the green one. This is the plus h vector multiplied by 0.38. This is the minus h vector multiplied by 0.92. So that minus sign can go here or here. Good. Now here's some math. I know most of you, all of you know this kind of math. In the book, I don't go through this math, but if you take 22.5 degrees, take the cosine squared, and add to that the sine squared, you get 1 exactly. Okay. And it turns out that it's nice to do math like that, but I find that for beginning students, it actually just confuses them. So I just avoid that. Here's the cartoon. And here's where we talk about superposition and coherence. So when we have two vectors, v and h, which are adding together in a synchronized manner, it's a coherent manner, we call this a superposition. So v and h are in superposition. And together they create the dipole. And then in time they oscillate. Now here's an important word in quantum physics, decoherence. If I have a good coherence initially and they're oscillating nicely together in phase, and then suddenly something bad happens, which is a decoherence event, it can randomly flip the phase of one of these vectors to the wrong direction. So this event I've illustrated, it flips the horizontal from minus the horizontal to plus horizontal. So it should be minus right now, just like up here, it should be minus horizontal. But it got flipped by some bad physical event. You know, something hit it, something jiggled it, an atom jiggled the photon or something. And so now it's starting to oscillate at minus A. And this can continue on, and you can have many decoherence events, and it can just randomize the oscillation and destroy the synchronization. In quantum computers and other quantum technologies, this kind of decoherence event completely destroys the ability of quantum devices to function properly. Okay, I'm going to end the poll there and show the results. So there's a bit of a spread here. You can see quite a large spread. That's good. That means you're learning something. you're going to learn something. If you knew all the answers, you wouldn't be learning. So let's think about this. There's a single photon here. The fact that it made it through this polarizer means it's depolarized. Its polarization is tilted at 45 degrees. And I just want to run the poll again. Go ahead and answer again. And remember, the calcite crystal is a linear optics device. It's very different from the crystal on the left, which is a nonlinear crystal. Okay, I'm going to end there. And I'm going to share the results. So most people said that either detector can click with equal probabilities, and that is correct. Very good. And the reason, this introduces a whole new concept, so I didn't expect you to necessarily know the answer to this. This is, think of this as an experiment that somebody did, and they said, oh, gee, look at that. Only one detector clicks, but either one can click with equal probability, but never does both detectors click. So that means that this calcite crystal is not able to split this photon into two photons like this nonlinear crystal could do. This is a red photon, and what emerges here is still a red photon, but it emerges either in the upper beam or the lower beam with equal probabilities. But that photon cannot emerge from both beams because they're mutually exclusive, and this is a linear optical device, which is an analyzer or a sorter. If I rotated this crystal so it was a DA sorter, and I put D in, then the photon would always go through 100% without getting deflected, because it has no component of A, which would be the lower beam. So I hope you're starting to get that point there. The detection probabilities depend on the quantum state of the photon. If I were to rotate this polarizer so it was H oriented, and then I waited until a photon got through, and this was an HV analyzer, the photon would always go through on the H beam, because I prepared the state of the photon by rotating this polarizer and waiting for it to go through. And as Feynman said, the photon forgets what it used to be back here. If it gets through, it has the new state defined by the polarizer that it just went through. Okay, so we use the word state. Let's talk about what state means. State means condition. Like when in the United States, we have the thing called the president gives the State of the Union address. He or she is describing what the condition of the country is. Okay, a classical state, in classical physics, a state is a list of everything that's possible to know about a particular object. And it permits you to predict precisely what's going to happen in any observation in any chosen measurement scheme. Okay, classical physics is not exactly deterministic, but in many cases you can predict precisely, like the trajectory of a baseball. You can predict it almost exactly. In contrast, a quantum state is a representation of everything that's possible to know about a quantum object. And it's an interesting way to say it because it's not possible to know as much about a quantum object as you can know about a classical object. And because you can't know that information, you cannot predict precisely what's going to happen, but you can still calculate probabilities. As we saw in the previous example, 50% probability it could hit one detector or the other one. And these events are what we call inherently random. In other words, there's no underlying hidden mechanism or clockwork that is determining which outcome will happen. As far as we know, I believe Feynman agreed with this, that there's simply no mechanism. It just happens. It's just random, and it's a property of nature that things can happen randomly without any underlying cause. Of course, you have to set the experiment up. If there's no photon, you won't see a detection. But given a set of sufficient conditions, you can see one outcome or the other outcome with no underlying reason or purpose. Well, this kind of uncertainty, relates back to Heisenberg's uncertainty principle. This kind of uncertainty actually helps you in doing things like making information transmission secure. And we'll talk about that next week. Okay. So a classical state represents actualities. It's describing exactly and actually how the world is. Whereas a quantum state doesn't represent actualities. It represents what Heisenberg back in the old days used to call quantum possibilities. But we no longer use that word in physics research. We have other words for it, but I like the term possibilities because it's not the same as a probability. A probability is just a number that you come up with somehow that describes how confident you are about a certain outcome, like polling for a presidential election. You can see the probability that this candidate will win or that candidate will win. But the quantum possibilities are very different. They have to do with the linear superposition or the superposition of different vectors in different directions. So we'll talk more about that. Okay, photons. Here's a zoom pole. A baseball can be hit and can travel through one of two holes in a wall to reach the glove where it doesn't go click, but it goes smack. And the question is the situation described best by a classical state or a quantum state? Let's run that poll. Launch poll. This question goes a little bit beyond what I said on the previous slide. I said on the previous slide that classical states could allow you to predict precisely what happens. But now in this example, I go beyond that and think about something a little bit different, that in the classical case, like if you told Newton about this experiment and he had a cricket bat and a cricket ball and he hit the ball and then somebody caught it on the other wall, Newton could say, well, it went through one hole or the other, but I don't know which. And he knew nothing about quantum physics. So he would still describe that by a classical state. But in his case, he would describe it by two possible classical states. He said, I just don't know which one it was. Okay, so I think the question was a little bit ill-formed based on what I told you before. So what I'm going to do is just go on and say that there's a classical state and explain why I say that. So even though there's two possible classical states, what Newton would believe for a baseball is that the ball went through one hole or it went through the other hole. But it certainly didn't go through both holes. So there's a kind of a classical uncertainty about what the state was. But whichever the state was, it was a definite actual state. So it's not a quantum state. Something as large as a baseball would never be observed to be described by a quantum state. The largest object that's ever been observed in a quantum state, I believe, is a large molecule. By large, I mean small molecule. A molecule made of many atoms, but it's not made of a size of a baseball. So a baseball is always in a definite classical state, but you may not know which one that was. So there can still be uncertainty, but we call that classical uncertainty. Different for an electron. If I have a single electron and I launch it towards this wall and I detect it on the other side, in that case, it turns out you cannot say that it went through one hole or the other, and you simply don't know which hole it went through. That's just a false claim. We believe that that's not true. Yet I also don't want to say it went through both holes. What I want to say for a single quantum electron is that that's a meaningless question. It's a question with no answer. The question, which hole did it go through? It's a question that's an ill-posed question. The question doesn't make sense. And I'll try to convince you later why I claim that. Okay. I have a weird scheme here. So quantum possibilities have different meaning than classical possibilities. Classical possibilities just mean it could have been in that classical state or this other classical state. Whereas in quantum mechanics, we have superposition, which is a very different thing than classical possibilities. Because in quantum mechanics, you can be in a superposition of two possibilities. And the example would be when I have a depolarized photon, that's a definite quantum state. But if I put it through an HV analyzer, it can come out in one beam or the other. And if it comes out the H beam, that doesn't mean that it was in the H state before it went to the crystal. It was in the D state. It's not the same as the H state. So when you observe that, you're not determining what the state was because, as Feynman said, it forgets that after it gets analyzed. It becomes a new state, and that's the one you detect. So measurement changes the state in a quantum situation, which is not true for the classical situation. So they're very different. And for a single photon, the quantum state of polarization is represented by a polarization arrow or vector. In the book, I always use the word arrow, but of course we know from the Despicable Me cartoon that a vector represents an arrow with a certain magnitude and direction, or rather the vector is represented by an arrow. Now here we say that the vector represents a quantum state. And here I've just shown one example. This red arrow is labeled psi. That's the name of a quantum state that we always use. And it can be pointing in any direction. And so it's not a physical, it turns out it's not a physical thing. It doesn't mean that for a single photon, it does not mean that the electric field is oscillating only along this red diagonal line. In fact, it's an ill-posed question to ask, along which line is the photon's electric field oscillating? This may seem strange because in the classical case, it was pretty obvious that's what we were talking about. But here, just like with the electron going through two holes in a wall, that's an ill-posed question. But we can still do the experiment, right? You put a photon in, you get a click, and you say that's the result. But to try to describe that underlying physics in terms of the direction of oscillation is actually not valid. So I didn't mean to mislead you. I meant to give you a classical analogy and say that when you go from a light beam with many photons, which acts classically, down to a single photon, the whole situation changes. So instead of the arrow representing the actual polarization of the photon, it represents the quantum state of the photon. And it's still a well-defined arrow, but it's not used to describe how the electron is oscillating. It's only used to describe the probabilities that you will predict experimental outcomes with. Okay, psi, the P is usually silent, so it's pronounced psi, but some people put the P on it, psi. It always has a length of 1. Why? So yeah, the quantum state is not a property of the photon, it's the description of the photon. And here we get to Max Born, who was one of the founders of quantum physics back in the 1920s. He figured out, when he was still quite young, probably in his early 20s, that the way to think about this quantum state, psi, is it's a mathematical object, it's a vector, and it's used only to calculate the probabilities of measurement outcomes. So for example, if we have the state psi for a photon that's been prepared in this red arrow state, if we analyze that with a polarizer whose axis is along this angle, we want to know what's the probability that photon is going to pass through that polarizer. Born said, you project the tip of the arrow with a right angle line onto the polarization axis. You measure the length of that segment, which has a length of A. That's what I called earlier the length factor. It's the length of the projection now. And then we square that number. That's called Born's rule. It works perfectly in every possible case you can imagine. Any experiment in quantum physics for any kind of a system whatsoever will follow this rule perfectly. And it's been tested probably to 8 or 9 significant digits. So it's really precise rule. We don't know why it's true exactly, but this is the best way to model the physical world. Now, if you were to rotate that polarizer by 90 degrees, so it's over here, we call this a complementary polarizer axis. So for example, this one could be D, and this other one could be A. And this photon polarization state could be whatever it wants to be, whatever you prepared it in. So to get the probability that it's detected if it goes through this other polarizer, this is now a different polarizer, you project the psi onto that axis at right angle, you measure that distance B, and you square it, and you get that probability. And nicely enough, A squared plus B squared is 1. So the probabilities add to 1, which they should, because if this picture represented a calcite crystal where there's 2 output beams, then you can have the photon emerging from one beam or the other. And the probability it emerges from one beam is A squared, and the probability to emerge in the other beam is B squared. And those probabilities have to add to 1. That's why we always say, or assume, or specify that the length of this state vector is 1. Okay, now.
Dr. Raymer,
Yes.
there's a question in the chat that's asking, what is the significance of the angle of the polarizer axis?
Yes, what is the significance of the polarizer angle axis? Well, so you remember when I was doing the demonstration, I had my plastic polarizer in my fingers, and I could rotate that polarizer any way I wanted. So that axis is by your choice. You, the experimenter, decide or choose what the axis is going to be. So let's say that Amy prepares a photon, and she can choose the preparation. So she chooses the angle of the red state vector, and then she sends that photon to you. Now you want to analyze that photon. You have to choose how to rotate your polarizer or your calcite crystal to make the measurement scheme of your choice. So there's nothing that chooses it other than your own preference. And if you repeat this experiment many times, maybe Amy sends you that same state of a photon 1,000 times, you can try analyzing that photon with many different polarization analyzer axes. And here I'll just show one example. Okay, now here I point out that Pythagoras, of course, knew this mathematical theorem, and on the right-hand side is a very cool picture of a clay tablet from 1700 BC illustrating the Pythagorean theorem. Of course, he didn't know about Born's rule. That didn't come about until the 1920s. Let's see. Now we could do this. Let's try this Jamboard exercise. This one might be a little bit challenging. So I'm going to do it partly and then maybe leave it for you as a homework to sort out as time goes on for the next session. Okay, here's the Jamboard. So a photon with polarization state minus A, which of course is the same thing as A, but it's nice to pick one at a certain time is pointed in the minus A direction, is subject to a sequence of polarizers. Here's the horizontal one. We know from what Feynman said, it forgets its earlier polarization and it comes out H, because these are the slots, not the wires. It comes out H with a certain probability. It's not 100% sure it's going to go through that H because it's not in the same orientation as the original photon state. Now it's H. Now it goes to an A polarizer, and it comes out A or minus A or plus A. In this case, I've shown it as minus A. It forgets its H value and it comes out A, or else it gets blocked, it doesn't come out at all. But if it comes out, it's now in a minus A state. And then it goes to a V polarizer and it tries to go through that polarizer. If it succeeds in going through, it comes out V. Now you see the state arrow is a little bit shorter now. So it starts out with a length of 1, and I show that down here in this graph paper. So here's a graph paper. H is on the horizontal, V is on the vertical, diagonal is here, minus diagonal is here, A is here, minus A is here. Now I put it into the minus A, so I said my photon starts out in this direction. This polarization state is pointing in the minus A direction. And its length is 1, because initially its probability is 1. But later on, the probability is not equal to 1 that it comes all the way through. The probability is going to be the square of the length of this vector here. But how do you use this diagram to figure out what happens? It first gets projected onto the H, then it gets projected onto the A minus A axis, then it gets projected onto the V axis, and when it finally gets to the end, it has a certain length, which is smaller than it started out with. So let's go over to the Jamboard and take a look at that. Whoops, that's the wrong thing. How do I get out of there? The Jamboard. Here's page 1. That's the problem. And this is A through F people. You have to work together on this. And then the next page 2 is G through L people, work together. And then page 3 and page 4. There's only 4 pages, so you have to work together. Now here's a trick. Oh, it says here, to draw a straight line, use Shift Draw. Watch this. Here's a wiggly line. But if I press Shift on my keyboard and draw, I get, didn't work. Whatever. Shift, draw, I get a straight line. See? So try drawing some straight lines on this screen. Yep. And now, that's good, I see one. And now go on to the graph paper, draw a straight line from the tip of the A arrow, of the state arrow, which is shown in blue here, project it onto the H axis with a right angle at the H axis. Somebody give it a try. I can watch what you're doing. Okay. So, and draw the little right angle square or 2 lines to show people what you've done, if you can. And it's actually better to use the straight click Shift Draw, because we're going to make this quantitative. In other words, we're going to use the graph paper. When we get the final vector, we're going to measure the length of it using graph paper and then square the number. So if you could erase that hand-drawn version, thank you, and then use the Shift Draw method from the very tip of the blue arrow. And that's not accurate. Try that again. Unfortunately, you have to, there's something called undo. Where is that? Okay, try to, yeah, there you go. Try drawing an accurate line directly to the H axis. That one looks good on page 1. And on page 2, that looks good. And now from the point of intersection between your straight line and the H axis, now you have to draw a line that projects it back onto the A axis, because we're now going through our second polarizer, which is the A. I'm looking at page 3 now. Try to draw a good line there. Nope, that's in the wrong place. It has to start at the very tip of the blue arrow on page 3. So you can erase that one or leave it there and draw another one. I see nothing on page 4, but maybe there's nobody in that name category. Oh, no, on page 3, that is not correct. It has to be at a right angle when it intercepts the H axis. So try that again. Page 3, that is correct. Now draw a line from that intercept point on the H axis to using a right angle to project down onto the blue A axis. Oops, page 1 got messed up. There you go. It's okay. Oh yeah, I see. I should lock down those figures. Sorry. Can I grab this? So that second line there, that magenta line, is not correct. On page 1, we want to draw a line from the point where, oh, I see, that's the state. Yes, yes. That magenta line is on page 1 is the new state, which is H, and it forgets the old one. Now take a line from that magenta arrow tip and project it onto the minus A axis at a right angle on page 1. On all your pages. Project now onto the minus A axis. And use the shift draw method to get, if you can, to get an accurate representation. On page 1, somebody just erased a line which was actually correct. So redo that. Good, good, perfect. Okay, page 2 and page 3, you have to draw that straight line projecting onto the minus A axis. We're not counting boxes yet. On page 3, the first projection is a little bit wrong. It should be lined up with the tip of the blue arrow at the bottom. We want to be precise here. So erase that line on page 3. And unfortunately, you can't move it. You have to erase it. Project it onto H and then project onto A. Page 2 looks good. Page 3 looks good. But now we have one more projection to do. Page 1, correct. Correct, that is the new state vector. Yeah, the red one, your drawings, the new state vector, very nice. And now measure the length of that final state vector and square it. Okay, page 2, you have a good projection on the A. Now project that one from the blue intersection point over to the V axis. Page 4. It's basically, the first 2 lines on page 4 are basically correct. The third one is not correct because you want to project that third one onto the V axis. And if you want to be precise, you should use the shift click, or the shift draw method, not the freehand method. Okay. Can't get the straight line function to work, but I do know. Okay, somebody on page 1 cannot get the straight line to work. I found that using my finger on a trackpad wasn't very reliable. If I use a mouse, it's more reliable, or a pen tablet. So Page 1 now has a good possibility. Okay, page 2 is looking pretty good. Page 3, we haven't done our second projection yet. Try to do that if you're still with us. Page 4 is just trying to redraw them more correctly, and somebody put an answer there, which I like, but we need to have the drawings on page 4 as well. Yeah, if you're having trouble with this shift draw, let us know in the chat box, because it would be nice if people could make this work. In the chat, Alex is asking, what is the significance of the angle of the polarizer axis? Really, there's only one polarizer axis. It's just tilted in a certain direction. And it's like in algebra where you have
Dr. Raymer,
yes.
you already answered this question previously.
Did I? Let me answer it again. Thanks. It's like in algebra where you have an x-axis. There's a 0, and there's a positive x side and a negative x side. But physically, they mean the same thing, but they're used for the mathematical treatment. I see on page 4 now, we're looking pretty good, except that second projection is not a very good right angle. It's pretty close, and that third one is pretty good as well. So now measure the length of your new state, which is, I'm going to draw it here, this here. Yeah, that's your new state there in the V, on the V axis. Measure the length of that new thing just by counting boxes. And yeah, when I say count boxes, fractions of boxes are okay, of course. 1, 2, 3, 3.3, 3.4, 3.5. Numbers like that are fine. Okay, page 3 has to draw the next projection horizontally over to the V axis on page 3. Not down that direction, no, delete that. Yes, except it has to be more accurate. Has to come exactly, so delete that green line and draw a really nice projection over there. Or just put a tick mark where you can see it's going, right? It's trying to go here, right? I made that mark there. It's not this one. Okay, good. So now we have the final polarization, and the answer posted on page 2 is not correct because the maximum scale is over on the left-hand side. You see 0, +1, and then 0.5, and down below it would be -0.5 and -1. So the scale is between 0 and 1, not between 1 and 10. So this number 12.5 is not correct. We want the length of that final state vector, which is this. What's the length on page 2? What's the length of that final vector? Okay, on page 1, we have good drawings, but we don't have a calculation yet. So you need to measure the length of the arrow on the V axis and then square it to get the probability. Page 3, that's not correct. The length of the final V vector is I'm going to draw an arrow here. There's the final V vector. Its length is something between 0 and 1. So if I square it, I could not get a number bigger than 1. And on page 4, I see a proposed answer, but I doubt you could get it that exact from the drawing. So if on page 4, if you can actually measure or count the boxes of this final length of this V vector and square it with a calculator, I'd like to see what that numerical answer is on page 4.